Good morning, everyone, and welcome to this morning's talk, Genealogical Bioinformatics, an introduction. What is it and why should you care? I'd like to thank Tim, the GFO and Portland chapter of International Society of Genetic Genealogy, for inviting me to speak today. I'm familiar with a number of the speakers you folks have had in the past and people who will be addressing you in the future, and I'm delighted to be in such esteemed company. I am Arun Konanur. As you can see from the attractive logo on the screen here, my little corner of the internet is discovering new ancestors. I invite you to visit the website whenever you like. There are a number of downloadable resources, as well as further information about some of the processes that will be covered in today's talk, and all sorts of interesting materials, case studies, and other things to peruse in your spare time. I'd like to begin by telling you a little bit about how I came to develop the tools that I'll be discussing over the course of today's presentation. After making use of the usual genetic genealogy workhorses, such as the shared centimorgan tool and what are the odds and so on, I found I still had a number of brick walls in my great-great-grandparents' generation and earlier that weren't working out for me. And even though we're all more or less obliged to work within the confines of 40 centimorgans and other things like that when it comes to autosomal matching, I couldn't help but feel that I was kind of leaving money on the table where my DNA matches were concerned, because my 40 centimorgan and greater matches were only about 3 to 5% of the total DNA matches I had. And I kind of intuitively knew that there were answers in the vast 95% of my matches that I wasn't able to analyze that would have information for me if only I could read the tea leaves correctly. And so I started working with ideas that eventually led me to some of the tools I'll be talking about here. I've filed, I think to date, 3 patent applications for these bioinformatic processes that I've developed, and I'm currently writing up my 4th application. The idea with a lot of these tools is that I think of them similar to how a carpenter might think of tools. They are very task specific, but they're quite interchangeable. You can use them in various combinations. And of course, a lot of the discovery is in finding new ways to use these tools. So we'll try to sort of talk about these things and explain them a little bit and see what we can get up to. To jump right in, genealogical bioinformatics, what is it and why should you care? Well, it's an excellent question. And indeed, the reason I originally suggested this might be a useful topic to present is that genealogical bioinformatics is something that has occupied my attention for almost 4 years now. But yet my feeling is that it's something that's kind of flown under the radar of most genealogy professionals. And more than, say, getting all of you to rush out and start doing this kind of work on your own, I very much wanted to use this opportunity to bring this topic to your attention, to raise awareness of the field, and to get folks thinking about which long-standing problems and issues in genetic genealogy might be addressed through genealogical bioinformatics. As for what it is, well, I'm afraid that much you could have gleaned from my synopsis. Genealogical bioinformatics is how future challenges in genetic genealogy will be solved through AI. And that, in a nutshell, is what I'll be discussing, using the process of developing my most recent bioinformatic process, the one I've already filed, my 3rd process, as something of a case study. So I'm going to leave the synopsis on screen for a moment to emphasize that this pronouncement, large as it is something I sincerely believe. Genealogical bioinformatics is how future challenges in genetic genealogy will be solved through AI. Why, you may ask? And there are 3 reasons that I believe this is the case. First, the widespread and ongoing development and acceptance of AI systems and methods among the general public. At this point, it's pretty much a given that even if you haven't yet employed AI as a tool in your own genealogy research or in other aspects of your life, you're aware that these tools exist, and you probably know someone who has productively employed or at least played with one or more of the AI tools such as Claude or ChatGPT or so on that are freely available on the internet. I'll give you a brief example of just how quickly things have evolved. In 2021, I filed my first patent application for a process I call CMA, and it's a bioinformatic process that uses set theory to curate DNA matches, and I'll talk about a little bit more later. And when you're filing a patent application, you want to cast as wide a net as possible in describing possible uses and applications for your idea so that you're more or less, you've staked your claim to this intellectual territory if someone in the future comes along and decides to use your idea in a manner that you didn't fully anticipate. And so in filing my application, I mentioned that the CMA process I developed employs axiomatic set theory, and that axiomatic systems can form the basis for machine learning and AI. And at the time I stated that in 2021, it really felt like I was talking about a future with flying cars. And I didn't really think I'd seriously revisit the AI implications of this filing within the next 10 years. But very soon, really within 18 months of filing that application, things changed. And we have AI tools that are freely available on the internet, and there's all sorts of things that are coming along. So what we imagined would be in the distant future is really very much here with us now. The second reason why I think that this is going to be the case is that we have what I would describe as a critical mass of DNA test data in the data sets of our testing providers, and the public has shown a desire to do more with this data. Not only have millions of people purchased DNA tests from various providers, but the genealogical community as a whole has recognized the importance of getting our eldest generation tested now while they're still among us. And as such, almost anyone taking a DNA test today will have a list of several thousand DNA matches who in turn have thousands of matches of their own, so that we are all essentially embedded in a kind of fabric of genetic connections and associations, even if we're only peripherally aware of their significance. Bioinformatics data mines the latent potential of these connections, as we'll discuss in today's case study. The genealogical public's desire to do more with the data our testing providers hold is evidenced by the enthusiastic reception afforded things like Ancestry's Pro Tools and enhanced shared matching, although, as we will also cover, sometimes access to this enhanced data brings with it additional problems. Finally, we have the emergence of bioinformatic expert systems, which is actually what we'll be discussing at length over the course of today's presentation. Now, before we get to all the good stuff, a word from my legal department. The various bioinformatic processes I'll discuss in this presentation are patent-pending processes from my little business, Discovering New Ancestors, Inc. All rights are reserved. This presentation remains the intellectual property of Discovering New Ancestors. Permission is granted for personal, non-commercial use of the processes via the desk-type prototypes, which are available through my website at discoveringnewancestors.com. But commercial and database management systems implementation of these processes require prior written approval. And what this means, of course, is that you're welcome to use anything I'm talking about here for your own research. But if you're going to do something commercially with it, or if you happen to work for some big DNA testing provider, then of course I'd like to hear from you first. You can find more information about everything I get up to genealogically at discoveringnewancestors.com. So just so we're all on the same page, I'm going to begin with a very brief discussion about AI. And now everyone knows what AI means. It's artificial intelligence. And specifically, when we say AI these days in the social sciences community, we're talking about generative AI. That's certainly the case for the most part where genealogists are concerned. A generative AI can be used to query, extract, process, tabulate, or synthesize data in various formats. So as an example, let's say if you had a collection of old handwritten wills, you could ask AI to convert their old style writing into readable text. You could ask AI to extract family trees from the contents of those wills. And then you could ask AI to connect those trees to possibly form larger networks of individuals and so on. And these are all tasks which are generally basically achievable now, as long as you take the time to engineer the correct prompt and so on. And when we think of AI, people tend to think of it as this single monolithic thing, but it's not precisely that. There are many components and subdisciplines which go into any AI tool. And each of these topics are worthy of their own presentation. But the topic I'm most interested in touching on today, the one I mentioned previously, are expert systems, which you can see there in the middle of the graph. Expert systems are, simply put, computer systems emulating the decision-making ability of a human expert. And expert systems aren't anything new. In fact, it's just the opposite case. If we were to look at this timeline here of the evolution of AI, you can see that expert systems are a feature of what was called the second AI boom, which actually happened in the 1980s and 90s. And expert systems were among the first truly successful forms of AI software. Just to give you some perspective, at the left side of this diagram, GeoFAI is good old-fashioned artificial intelligence. And if you're old enough to remember, let's say, machines in the 1960s that knew how to play tic-tac-toe, that's what we're talking about there. Interest faded in the 1970s as programming languages and technology evolved, and that was called the first AI winter. As I mentioned, expert systems were a feature of the second AI boom. And then in the dot-com era, interest in AI faded again, and that's what we call the second AI winter. And now, of course, there's all kinds of things happening in the field, and it's generally agreed that there probably won't be a third AI winter because artificial intelligence is very much here to stay with us as far as we can see. If expert systems were a big deal 40 years ago, why am I talking about them now? And there are several reasons, really. First and foremost, where DNA matches are concerned, there was nothing resembling consumer DNA testing in the 1980s, so there couldn't very well be expert systems for organizing DNA matches then, of course, could there be? Additionally, of course, since the second AI boom, in fact, some genealogical expert systems have been developed. As an example, Ancestry's Throughline or MyHeritage's theory of family relativity are examples of expert systems in that these are computer systems that make decisions that a human might also make, and they exist already for us to talk about. What's missing so far are what I'm going to describe here as bioinformatic expert systems, and hence, again, that's what we're going to sort of cover off here as we go. So what are they? Well, expert systems, as I said, are computer systems emulating the decision-making ability of a human expert. Expert systems are designed to solve complex problems by reasoning through bodies of knowledge. Bodies of knowledge are basically the sorts of things that we already know about a field, whether it's genetic genealogy or whether it's driving a car or what have you to talk about. And these systems are typically task-specific, but they can form the building blocks of more advanced systems. And this last point is something we'll return to later in the presentation. Returning to the semi-rhetorical title of why should you care about genealogical bioinformatics? Well, the ability to express genetic genealogy's body of knowledge, one modular concept at a time, in terms which allow a computer system to effectively become a subject matter expert is what makes genealogical bioinformatics so appealing and so very powerful. In fact, as you'll see from today's case study, the ability of bioinformatics to address long-standing problems in genetic genealogy actually means that we're extending genetic genealogy's body of knowledge as we develop these tools. And so now we come to the $3 word that I've been kicking about, and you've probably been wondering, what precisely does it mean? Bioinformatics. Now, just what is bioinformatics? And by extension, what is genealogical bioinformatics? It's a little disingenuous, but where genealogical bioinformatics are concerned, I'd like to put question marks at both ends of the phrase like they do in Spanish, because neither genealogists nor scientists really have a good idea of what's going on in this field. By that, I mean that genealogical bioinformatics is best regarded as a hybrid discipline of a hybrid discipline, which again raises the question, well, what is bioinformatics? And here's a definition. Bioinformatics is an interdisciplinary field of science that develops methods and software tools for understanding biological data, especially when the data sets are large and complex. Now, our biological data are DNA matches, and certainly when you think of the millions of people who've tested and the fact that any of us probably have 10,000, 20,000, 40,000, 100,000 DNA matches in our full set of matches, we are dealing with very large data sets and they're complex. Now, bioinformatics, for our purposes, we're combining the disciplines of biology, information engineering, and mathematics into bioinformatics. And unless you're going to design your own software tools, you really don't need to know anything about these last two fields. There are days where I'm not certain I personally know anything about these fields, so you're a pretty good company if you don't either. If you go to Facebook and look online for a group about bioinformatics, you will find a whole lot of science PhDs asking questions about in vitro enzyme engineering and biocatalysis, or calculating polygenic Rusk scores, and other such topics, which are in no way remotely germane to genealogy, which is why when I speak of genealogical bioinformatics, most scientists look at me like I'm crazy. In fact, sometimes when I have tried to post to these groups to explain what it is I'm doing, the moderators don't even accept my post because it's really not what people are thinking of in the hard science area. So perhaps to them I'm crazy, but I'm seriously not. When we speak of genealogical bioinformatics, we're talking about a discipline that uses biology, information engineering, and mathematics to address problems in the field of genetic genealogy. which I'll admit is something that not very many genealogists are familiar with doing either. Now, at this point, some of you may be wondering what precisely it is you've gotten into, but let me assure you, you already know all the biology you need to know because we're talking about biology as it pertains to genetic genealogy. In fact, each of you probably know more about genetic inheritance than you will need to cover off anything we're going to talk about today. As for the information engineering component, that's essentially just taking a familiar problem, something we've all worked with in genetic genealogy, and looking at it in a variety of ways. And as for the math involved, it's not actually number math, at least not really. It's mostly logic and expressing familiar genealogical principles in a way that a computer might understand. So you won't need to bust out a calculator or anything like that. Let's begin our introduction to genealogical bioinformatics with a case study that illustrates how this field can be used to address a long-standing problem with shared DNA matches. We'll begin with a little background to this problem, as we've probably all encountered it at one time or another regarding our shared DNA matches. Let's say you, or a relative or a client, takes an autosomal DNA test, and you've received your test results. We'll keep everything here as generic and anonymous as possible, so we'll call our test taker subject A. We'll illustrate their DNA matches with a yellow circle. And now let's suppose that subject A took their DNA test because their second cousin B already had taken a DNA test. And so we can think of subject B here and their DNA matches as the blue circle. Now, of course, since A and B are second cousins, and really, if they match each other at all, then we can think of subject A's DNA matches and subject B's DNA matches and whatever matches they have in common, as illustrated by the green area where the circles overlap. We can refer to the DNA matches common to both A and B as shared matches. And these shared matches are other individuals who took a DNA test and just so happen to share DNA with both subject A and subject B. We can designate them as subject C, subject D, subject E, and so on, for however many people happen to match both subjects A and B. There could be just a few people who match A and B, or there could be hundreds. Now, I warned you there would be math, but it's not going to be number math, so here's a little bit of that. We can refer to the matches shared by both A and B as the intersection of A and B, or A intersect B, which we write like this with the little upside down U. And if we want to talk about how many people match both subject A and B, we can talk about the magnitude of the intersection of A and B by putting these vertical bars around the A and B intersection notation like this. In fact, we can talk about the magnitude of each of these color areas. So we could say the magnitude of A is, let's say, 13,582 DNA matches. We can say the magnitude of B is 18,900 DNA matches. And we can say the magnitude of A intersect B is 940 DNA matches. Those would be 940 people who match both subject A and subject B. Now, we're all more familiar with seeing our DNA matches in a list format like this one here, which is obviously a redacted layout taken from Ancestry. Here you can see we have subject A's DNA matches, and that A has two close family DNA matches, subject B sharing 766 centimorgans of DNA, and subject C sharing 371 centimorgans. And the list continues down with two extended family matches, subject D sharing 315 centimorgans, and finally subject E sharing 129 centimorgans. Now, of course, the great thing about viewing these reports online is that we can always get more information. So we can click on subject E and then click on the highlighted shared matches link, and we can view the DNA matches common to subjects A and E. And here we see that subjects A and E, in addition to matching each other, also match subject B, subject C, and subject D. Each of these individuals, B, C, and D, are subject A and E's shared matches. Now, you're all likely familiar with what we describe as the utility of shared matches. And the idea is that here, if we take, say, subject D, and we know that subject D shares DNA with both subject A and E, well, then it's possible they might share a common ancestor as well. And more often than not, especially when our subjects share a significant amount of DNA, that is indeed the case. Of course, we can't just assume that's the case, so we'll want to examine subject A, whom I'll call the tester, and subject E, otherwise referred to as the match, and subject D, who we'll call the shared match, And taken together, these three individuals form a shared match trio. And since these particular test results are from DNA kits I administer, we can build up pedigrees for these individuals, or in this case, what are actually inheritance diagrams. And as we go back another generation and another generation, we see that yes, they do indeed have a common ancestor for our shared match trio, as we'd hope they might. And since in this case, the common ancestor is just an individual, we can go back one further generation to identify the common ancestral couple shared by our individuals. Now, it's great that we were able to find a common ancestral couple for our trio amongst the records in my family tree. But as we consider this type of shared match trio, in general, we're not going to be so concerned with the specifics of my family tree as we are with the fact that this type of shared match trio supports or favors research of our trio's pedigree to discover common ancestral origins. And so we'll call this type of trio a favorable trio. The idea is that we have three individuals, they match each other, and if we work their pedigrees back a few generations, we find they have a common ancestor, or more precisely, a common ancestral couple. And again, this is a favorable trio. Now, the favorable trio is the sort of match genealogists like to find because with a little effort, we're rewarded with new information about our ancestral lines, or at the very least, our genealogical records are validated by our biology. But of course, not all shared match trios are favorable, are they? In my family tree, adjacent to the favorable trio we've just encountered is an example of the other type of shared match trio. And in this trio, subjects D and E share common ancestors, just as they did in the favorable trio. But now we have a situation where the third element of our trio, subject K, shares a distinct common ancestral couple with subject E, and yet somehow subject K also shares DNA with subject D through a unidentified as yet common ancestral couple. And this type of shared match trio, which doesn't so easily reward building pedigrees for ancestral lines of its subjects, is known as an unfavorable shared match trio. And so among shared matches of practically anyone's DNA test results, we have favorable shared match trios and unfavorable shared match trios. The favorable trios reward modest effort required to build up its subjects' ancestral lines, while the unfavorable trios' pedigrees lead in separate diverging directions. They effectively raise more questions ancestrally than they can answer. The problem with favorable and unfavorable shared match trios, a problem that exists not only for us as genealogists, but also for DNA testing providers, is how precisely do we tell these two types of trios apart when all we see is a list of shared matches that Ancestry or another provider presents us? When we see shared matches presented in a list format like this layout here from Ancestry, there's nothing to indicate whether the shared matches listed are favorable or unfavorable trios. And the reason for this at the present moment is that our testing providers don't actually have a reliable way of distinguishing favorable shared match trios from unfavorable shared match trios. Now, any method of distinguishing favorable from unfavorable shared match trios needs to be both fast and accurate. So we can examine a few ways this might be done and see how they compare. Our first method is the arbitrary threshold, which DNA testing services have employed in the past. The idea is to report all shared matches above, say, 20 centimorgans, with the idea being that circumstantially, the likelihood of encountering an unfavorable trio tends to increase as the amount of DNA shared among the trio decreases. In other words, if you have three individuals and they all share 100 or more centimorgans with each other, it's very likely they will be a favorable trio, but smaller matches, let's say 15, 20 centimorgans between the three elements in the trio, are more likely, let's say, going to be an unfavorable trio. But again, there's no hard and fast rule. It's just kind of what we call an invidious distinction, a threshold we decide to make a cutoff at. Now, this approach is fast, as much as checking for 20 centimorgans of shared DNA doesn't take much time, but it's not accurate, as it assumes that all shared match trios above 20 centimorgans are favorable, and it accepts the proposition that we're willing to ignore shared match trios below 20 centimorgans of DNA. Now, we could use the genealogical method that I employed in my example of validating a favorable trio with individuals from my tree. We either find a common ancestral couple to all members of our trio, or we don't. Not surprisingly, this method is neither fast nor accurate, as in many cases, our DNA matches haven't constructed public online trees. And even if they have, these trees may be inaccurate. And if our DNA match is a result of a non-paternity event, then the available online trees may not accurately reflect that information. So no, the genealogical approach isn't going to work either. Now, genetic genealogy would seem to offer promise if we were to take a more granular approach and compare the shared segments among our trio in order to identify identical by descent segments of DNA. We might employ phasing to determine if the correspondences we're looking at are exclusively maternal or paternal as a way of distinguishing between ancestral lines that diverge versus lines leading to a common ancestral couple. As you might guess, I'm going to give this method half points in each category for several reasons. First, in many cases, especially if our tests are at Ancestry, we don't have ready access to segmental data to assess the possibilities ourselves. Further, my understanding of the matter is that shared segments will only get you so far, and not all favorable trios will necessarily share identical segments. Additionally, if shared segments were the way to go, I would expect that DNA testing providers would have already employed this method to flag unfavorable shared match trios, especially in light of the fact that now if you pay a monthly subscription to get additional shared matches beyond the 20 centimorgan threshold through Ancestry DNA's enhanced shared matches, you're now getting results which are unverified. And so at best, half marks here. So finally, genealogical bioinformatics as a method for performing shared match differentiation. And of course, we're going to withhold scoring this method for the moment because it's the topic of today's case study. Now to begin, I'm going to summarize what I've come to think of as the genealogical bioinformatic methodology, which is basically just a process that has kind of grown organically for me based on how I've found that the investigative process tends to evolve in practice in terms of what I do when I'm developing these processes. We begin by identifying the problem, which we have already done. Today's problem is, how do we differentiate shared match trios? We talked about the favorable and the unfavorable trio and how to look at them. We can intuitively see they're different, but we need to find a way of basically sorting those in real time so that our DNA providers can tell us what's favorable and what's not. Phase 2 in the methodology is to define and explore the problem's taxonomy. We'll address what that precisely means in just a moment, but the idea here is to systematically document the steps through which we obtain our shared matches. Phase 3, we'll mathematically model the problem and evaluate possible solutions. Phase 4, we prototype a solution, optimizing it for computational efficiency. And in this phase, we essentially build a working model of our process using whatever coding tools seem best suited to the task. Phase 5, we field test the prototype with real-world data. And having built a model of how our differentiation process might work, we test it with data from actual DNA tests. Phase 6, we revise the prototype as and if necessary, and repeat the process, if necessary, from Phase 3 onwards. If any of you have programmed computers before, either professionally or just for fun, you may recognize the last 3 phases of the methodology here, which are basically taken from what we call the software development lifecycle. So this is nothing I've remotely invented. This is just something that programmers do. It's not remotely original in this regard. Now, these are the steps we will follow to arrive at a bioinformatic solution to our problem of differentiating favorable from unfavorable trios. The successful execution of these steps in practice might take several months. In one case, I spent a little bit more than a year on one particularly challenging process that I'll mention later. The case we're going to review today took me about a month to get properly sorted out. But again, the solution is what's most interesting. So returning to our methodology, we've identified our problem. How do we differentiate shared match trios? We'll proceed with step 2 to define and explore the problem's taxonomy. I realize taxonomy isn't a genealogical term, and indeed, if you've encountered it elsewhere, it's probably been in the context of life sciences, where it means the classification of something, especially organisms. And if you were a biologist, that's pretty much what taxonomy means. However, in the context of bioinformatic methodology, our use of taxonomy will be pretty much as a data or process dictionary. And by this, I mean that since we already have a basic understanding of how we obtain shared match trios, we can express this systematically. Now, to review, our taxonomy is describing how we obtain a shared match trio, which consists of 3 distinct individuals: a tester, a match taken from the tester's roster of DNA matches, and a shared match common to both our tester's roster of matches and the roster of DNA matches belonging to the match. Let's begin by describing the sort of information we need in our taxonomy. We're going to need the name of the item or process we're describing. We'll want to assign a general classification to to that item or process. And we're going to want to assign a symbol or mathematical definition to that process just so that we can refer to it elsewhere and establish how these items and processes all fit together. So let's work through how we obtain shared matches, and this will be a lot clearer because we've all accessed our shared matches online. It's something we understand. Now, of course, nothing happens in genetic genealogy without someone taking a DNA test. So we'll start with that. Regardless of the company you purchase a test from, you get a raw DNA data file, the sort of file you can download from your provider and optionally upload to third-party testing services like GEDmatch. And if we were to describe what our raw data file is, it's just that. It's data. It's information which is tabulated or measured for us, and it's not going to change because it's something we've obtained from outside any kind of shared DNA match reporting. And if you think about how our raw autosomal DNA tests work from a genealogical perspective, we take the DNA test once, and assuming there have been no errors made in the lab, we don't need to retest in order to update our DNA matches because the raw data doesn't change, and we don't need it to change. We don't want it to change. So if we were to designate ourselves as individual A, then we can represent our raw data as A DNA, and that's a symbol we have there in the third column. Now, our DNA testing provider is going to have millions of DNA tests in its database in addition to our test. So we're going to need to refer to each test by some kind of unique name or identifier, just so that our data doesn't get mixed up with someone else's data. And even though our test ID isn't something we're aware of, you can understand how a commercial system with 10,000 people named John Smith needs to be able to keep track of each one separately. And because this information is something used to label or describe an unchanging data item, we refer to this type of information as metadata, literally data about data. And I imagine this term may be familiar to some of you because the term does turn up even in describing photographs and a lot of data assets. And of course, we kind of jumped the gun by designating our example tester as A, but that makes our tester's name A. And now, as you might imagine, our raw DNA data on its own contains a wealth of information about ourselves, but knowing that we have brown eyes or a propensity to go bald isn't all that genealogically useful. And so we need to talk about DNA we share with other people who've taken a test. And since we don't know who's going to match us and who doesn't, the simplest thing is to refer to anyone who has ever taken a DNA test with our testing provider, whether or not they match us, and that includes ourselves. And we call this collection the universal set. And just like the actual universe, it's immense. If your DNA testing provider has tested 26 million individuals, then that's how many individuals, what we can call elements, are in our universal set. Now, our universal set is a collection of individual items of data, and so we call it a data set. And we're going to symbolize it with the bold letter U in the DNA underneath it, similar to how we labeled our tester's raw DNA data. Now, you might be thinking to yourself, this is all great, but we don't actually interact with any of these invisible data structures. And you'd be correct. When we go to our DNA testing provider's website every week, or once a month, or whenever we want to see what's new, we're not looking at our raw DNA data because that doesn't change. We're looking for new DNA matches. And our DNA matches involve more than just our raw data. We need to compare our raw data to everyone else's data from everyone else who's already tested with our DNA testing provider. And we want to see who we share DNA data with. And in practice, those DNA matches have to be at or above a certain level of significance in order to be useful to us. Now, this is a different kind of information than our raw data, because while our raw data doesn't change from week to week, our DNA matches will increase as more individuals are added to our universal set. Also, the list of who we match isn't something determined in a laboratory. It's an outcome of our DNA match reporting structure. It's changeable, tabulated data, or manufactured information, if you will. And so we don't describe this as static data, but rather as something germane to our DNA reporting system. Some people might call this a facet, but I would prefer the term class, as it works better in mathematical set theory. And since these are our tester A's DNA matches, we'll designate them here as DNA with a bold A. That's our tester's roster of DNA matches. Now, of course, there's more. We said we need to compare our raw DNA data to everyone else who's already tested with our DNA testing provider. And we can express this mathematically by saying that our tester's DNA matches are their intersection of our tester's raw DNA data with the universal set. And that's what I've written here in the rightmost column, the intersection of A's DNA data with the big universal set of DNA data. We also said the DNA matches have to be of a certain significance in order order to be useful. So if we wanted to have a lower limit of, say, 8 centimorgans for our DNA matches, we could add this to our formula. Taken together, this says that tester A's DNA matches are the intersection of the tester's raw DNA data with our universal set, such that the vertical line means such that the linkage or shared DNA between our tester's data and the matching element of the universal set is greater than or equal to 8 centimorgans. Now, this pretty much describes what happens when we sign into our testing provider and review our DNA matches. We're just taking a moment to better understand the process systematically. So we have our list of DNA matches, and if we want to review any of one of those matches in detail, we can designate that individual DNA match with the letter B, such that B is an element of tester A's DNA matches, and that's what we've written in the symbol column on the right there. Now, with the unique ID selected for our match, we can generate a roster of DNA matches for our match B in a way similar to how we got A's DNA matches. We have B's DNA data intersected with the universal set such that whatever matches we find are greater than or equal to 8 centimorgans. And you can see that formula there on the right-hand column, which again is consistent with how we defined subject A's DNA matches. Now, with our matches roster of DNA data refined, we can designate our shared match C from the collection of DNA matches common to our tester's roster and the roster of our match. Now that we've defined the elements of our shared match trio, we can define the trio itself as an unordered collection of those 3 elements. And I'm going to return to what that means later, but an unordered trio makes intuitive sense since the shared match trio is either going to be favorable or unfavorable, regardless of how we order the individual matches within the trio. It's still either a favorable trio or an unfavorable trio. So the order we talk about our elements in does not really matter. Now, this is our taxonomy for a shared match trio, and it reads almost like a recipe with ingredients such as the raw DNA data and the universal set and processes we use to select our match and shared match and generate a roster of DNA matches for each of those individuals. What this taxonomy doesn't do yet is address the problem of how we're going to differentiate favorable from unfavorable trios, but here's where our carefully crafted taxonomy supports our investigation. Our taxonomy documents the systems and methods used to generate a shared match trio, which we have defined as an unordered collection of 3 individuals. And since our investigation wants to develop a bioinformatic way to differentiate favorable from unfavorable trios, we can imagine that this process will ultimately yield a differentiation value, something which determines whether a given trio is favorable or unfavorable. This could be a true-false determination, or it could be a number. We don't really know what it is. And since this differentiation value essentially labels the property of a class, our shared match trio, we can call this a metaclass. And right now, since we don't know really what it's going to be, we can just give it a letter name, V, and leave it undefined for the moment. Returning to our methodology, we can place a check mark next to phase 2 in that we've developed and explored the problem's taxonomy, and we can move on to phase 3 to mathematically model the problem and evaluate possible solutions. Now, mathematical modeling is the process of constructing an abstract description of a concrete real-world system using mathematical concepts and language. Fortunately, our carefully constructed taxonomy has essentially done this work for us. In the case of here, our symbol formula column contains all of this information with the notable exception of our differentiation value, which is still undefined. But basically, we have a mathematical model for all of the components and steps in our process. As genealogists, we can look at the diagrams of the unfavorable trio and the favorable trio, and intuitively just know that they're different, that they behave differently, that they each tell us different things about our ancestral lines. What we need to find is a mathematical way of expressing this difference. And the reason we need to find a mathematical way is basically because we want a computer to do the work for us, and computers do things very well with math. So one problem with finding a mathematical way to express the difference between our favorable and unfavorable shared match trios is that the more you know about math, the more ways there are to slice and dice all of this information. We could explore the linkage DNA shared between the elements of our trio. We could look at the statistical properties of how that's distributed. and so on. You could basically go on forever trying one measurement after another, hoping that something that works for one instance of a shared match trio would work for every trio, and then go back to the drawing board if and when it doesn't. Now, at the moment, that's how I'd imagine a generative AI would go about creating an expert system to perform shared match differentiation. It would try things. If it works, it works. If it doesn't, it goes back, and it just keeps doing this endlessly. However, I'm thinking we can do better ourselves, as our taxonomy provides important guidance conceptually where the formation of a differentiation value is concerned. Our taxonomy allows us to review how we came to obtain shared match trios in the first place. And my experience over the course of developing and filing patents for various processes, for 3 genealogical bioinformatic processes to date, has been that the most successful, the best bioinformatic models employ the formulas of the taxonomy as a basis for modeling a solution to our problem. In this particular case, arriving at a formula for our differentiation value. So in the case of our shared match trio taxonomy, we have tester A, who's an element of our universal set. We obtain our tester's DNA matches from the intersection of our tester's raw DNA and the raw DNA of the universal set. From within our tester's matches, we select individual B, and we obtain individual B's DNA matches the same way we defined A's DNA matches. And finally, from the collection of DNA matches shared by A and B, we select individual C, forming our shared match trio, which could conceivably be favorable or unfavorable. Now, you may have observed a pattern here. Begin with individual A, find their DNA matches, choose individual B from A's matches, find individual B's DNA matches, and finally select individual C from matches shared by A and B. But what if we don't stop there? What if we follow our taxonomy process one step further and we continue the process defining individual C's DNA matches in the same way we've defined A's matches and B's matches? With 3 sets of DNA matches, how would we describe the space in the center of our Venn diagram? Well, of course, the triangular area in the middle of our graph is the intersection set of all 3 sets of DNA matches, which is something we hadn't yet considered in our shared match trio taxonomy. Let's consider what the intersection of the DNA matches of all 3 individuals means for our trio. In concrete terms, we're asking who matches our 3 subjects. Since we know that A, B, and C all match each other, we can ask who else matches our 3 subjects. Of course, since we don't specifically know who has taken and who hasn't taken a DNA test, what we're really asking is who else could possibly match our 3 subjects. Now let's consider our favorable trio. We've got 3 individuals who share a common ancestral couple, and that's really the only restriction we have here. So long as another individual has a genetic connection to our common ancestors, they could potentially participate in this trio or add an additional element to our trio. In mathematics, specifically in logic, we call this sort of arrangement with just a single restrictive criterion an example of sufficient conditions, which is to say that a connection to our shared match trio is possible when any of the following conditions are met. And we can list and diagram a few of these potential connections. We have our 3 individuals sharing an ancestral couple, and very likely the descendants of those individuals would also share a connection to the same common ancestor. The ancestral line connecting our 3 individuals to their common ancestor is either a maternal or paternal line, so some half-siblings and all full siblings of our individuals would also share a connection to our common ancestor, along with their descendants. Other descendants of our common ancestral couple could also potentially participate in our shared match trio. And lastly, anyone who shares an ancestor with our common ancestral couple could also potentially connect to our shared match trio. So conceivably, there are dozens, even hundreds of individuals whose DNA matches could include the 3 subjects of our favorable shared match trio. And if we wanted to, we could take a census of the number of individuals who match all 3 of our shared match trio subjects and put them in a graph. And I've done this just to sort of help you visualize the group of matches that every element of our favorable trio might share. And you can see that the shape, the distribution of those matches kind of looks like this little blue curve on the right. And this shape more or less follows the distribution of your DNA test results in general. If you've ever browsed through your DNA matches, you've probably noticed that you have a few close matches, more second to third cousins, a greater number of fourth to fifth cousins, and then a huge number of small matches who might share 8, 10, 12, or 14 centimorgans of DNA with you. And we'd expect this collection of individuals who match all 3 elements of our favorable trio to follow the same sort of shape, but with fewer individuals than in our full set of matches, as not everyone listed in your DNA results connects to a single ancestral line. But again, I've drawn this curve just to give you an idea of the general shape of how all the people who might match a favorable trio would distribute their DNA. Lots of small matches and fewer large matches. Now, let's repeat this examination with our unfavorable shared match trio. Whereas the favorable shared match trio had 3 individuals connected by a single common ancestral couple, our unfavorable shared match trio has pairs of elements sharing a common ancestral couple. And since there are 3 distinct pairings of our 3 elements, we can see that the diagram of our unfavorable shared match trio shows 3 separate common ancestral couples. As a result, any individual who matches all 3 elements of our unfavorable trio needs to have a genetic connection to 2 of the 3 distinct common ancestral couples in the diagram. Now, because a single connection to a common ancestor is no longer sufficient, but rather 2 connections are necessary, the logical term for this arrangement is an example of necessary conditions. The favorable trio was an example of sufficient conditions, and these are necessary conditions. You may have, in other discussions, encountered the terms necessary versus sufficient conditions, and this is essentially what they mean. So with necessary conditions, multiple criteria must be satisfied. In the case of our trio, genetic connections to 2 distinct ancestral lines must be satisfied for an individual to match every element of our unfavorable shared match trio. And we can survey which genealogical connections might satisfy our necessary connections. Once again, descendants of our subjects will work nicely. If individual E has a genetic connection to 2 of our 3 common ancestors, then it's likely their children will as well. Not guaranteed, but likely. Full siblings of our subjects and their descendants would also satisfy our necessary conditions. In my patent filing, I explored how other types of close connections to our subjects are really just instances of this basic arrangement, but I'm not going to go down that particular rabbit hole this morning, so you'll just have to trust that I've examined this issue thoroughly. I'm also going to simplify things right here and go with a third criteria, individuals who match 2 of the common ancestors. And the reason for this is that apart from these close relations for our 3 subjects, when we search for individuals who match all 3 of the subjects in an unfavorable shared match trio, we find that these relatively close DNA matches, direct descendants and their siblings, and then we also see a large number of individuals who share a small amount of DNA with each of these subjects, but their connections to the elements of our trio are so remote that we can't even begin to determine the genealogical connection. So to summarize, there are comparatively few individuals whose DNA matches could include our 3 subjects in an unfavorable trio. They're either reasonably close DNA matches to our 1 or more of our subjects, or they're pretty distant matches. And you can see in the graph at right, if we were to take a census of the individuals who match all 3 elements of an unfavorable shared match trio, we see very few close matches. These are individuals who share a large number of centimorgans with at least 1 of our subjects. Then the number of individuals matching all 3 of our elements falls off quickly in the middle centimorgan range, and then it climbs back up on the left corner of the graph there, where distant matches are concerned. So here we have our diagrams once again, the unfavorable shared match trio on the left and the favorable shared match trio on the right. And below them, we have the rough graphs we've drawn to describe the number of individuals who match all 3 elements of each trio and how those matches are distributed with regards to centimorgans, larger centimorgans being on the right end of the graph. Now, if we wanted to summarize our findings, we could say that our favorable trio supports many connections in that many individuals can potentially match all 3 elements of our trio, while the unfavorable trio supports comparatively fewer connections. And further, if we were to characterize the amount of DNA the individuals matching the elements of our trio share with the trio, we could say that the individuals who connect to the favorable trio can exhibit a broad range of shared DNA with our trio subjects, whereas the individuals who match the elements of our unfavorable trio either share significant DNA with 1 or more of our subjects, or they tend to share a small amount of DNA owing to an uncertain genealogical connection. Now, if we were to compare the graphs we've drawn, the blue representing the favorable trio, the red representing the unfavorable trio, we see that they tend to converge at the extremes. Where close DNA matches sharing a large amount of linkage are concerned, both favorable and unfavorable trios tend to have similar tallies of individuals matching all 3 elements of their trios, because siblings and direct descendants will match either trio. Similarly, at the left end of the graph, where small DNA matches are concerned, individuals with distant connections to our 3 individuals also tend to pile up, owing to how shared centimorgan profiles for distant genealogical connections all tend to overlap. Now, if we were to shade in the area of our graph that represents the difference between favorable and unfavorable shared match trios, you can better visualize what I mean in terms of how the graphs converge converge at their extremes. Now, clearly, if we want to differentiate between favorable and unfavorable trios, it makes no sense to look at the extreme ends of the graph because there's not that much space between the two lines. And when we consider real-world data, the distinctions between our two trio types are more likely to be obscured. So what we want to do is look at the part of the graph where the distinction between favorable and unfavorable trios is greatest, which is in the middle centimorgan range. So we can set a low centimorgan threshold and a high centimorgan threshold as shown in the example, and tally the number of individuals whose shared DNA falls between those limits. Now, this sort of stratification or exclusion of certain DNA ranges is by no means as arbitrary as at first it might seem, nor is it unique to the shared match differentiation process. If you're familiar with clustering techniques, such as the Leeds method, these procedures also restrict the scope of their analysis, as close DNA matches tend to obscure constituent ancestral lines, and small DNA matches are unreliable indicators of ancestral pedigree. As such, we'll establish a lower threshold of 40 centimorgans for our DNA matches, and an upper limit of 400 centimorgans for the DNA matches we'll consider in our differentiation process. I arrived at these values through the analysis of actual shared match trios, but just as with any AI system, we could train this process using the matches from a commercial DNA testing provider's dataset and possibly arrive at a more refined value, or we could generate population-specific thresholds as well for certain endogamous populations. To clarify what we mean by these centimorgan limits, it's helpful to remember that an individual, we'll call him X, who matches all three elements of our trio will share measurable DNA with each member of the trio. So in the case of the favorable trio, we can speak of linkage X shares with element E, linkage X shares with element D, linkage X shares with element A. If any of these values are greater than 400 centimorgans, we'll exclude that individual from our tabulation. We'll express this by stating that the individual's maximum linkage to our trio must be less than or equal to 400 centimorgans. And at the lower threshold, that the individual must share at least 40 centimorgans of DNA with any member of our trio. Now, even though we've established what we're looking for and where we're going to look for it, we still have the issue of what we mean by many connections to our shared trio versus fewer connections to our trio. This is particularly important when we consider that some trios may include ancestral lines where many people have tested or where endogamy has boosted the number of shared matches, while other trios may have the opposite problems. And so when we speak of many versus few connections, we're making a comparison. But what exactly are we comparing the individuals who match our trio elements to? Once more, our taxonomy, reviewing how we've defined our trio, provides us with a workable answer. You'll recall, before we arrived at our three-element trio, we had a duo, I actually prefer the term dyad, consisting of the individual who took our DNA test and a match from their roster. In fact, you'll also notice that coincidentally, our two example trios share a common dyad between them. That's helpful in simplifying our illustration, but ultimately it's not required. Now, something we want to notice is that a dyad consisting of an individual and someone chosen from their roster of matches is by definition favorable. The only way you could conceive of an unfavorable dyad would be two individuals chosen at random who don't match each other, and that's not what we're talking about here. In the case of our trios, we have two individuals who match each other and therefore form a favored matches. And you can visualize how these shared matches are distributed from the green line in the graph at the right. What we want to determine is what happens to the shared matches of the dyad when we select one of those shared matches to form a trio. What we want to determine is whether adding a third individual from the dyad set of shared matches creates a favorable trio with a relative abundance of individuals shared by elements of our trio, or an unfavorable trio with fewer DNA matches common to its elements. In each case, we compare the DNA matches shared by the three elements of our trio to the number of individuals shared by our favorable dyad before it became part of our trio. The number of shared matches of our dyad will always be larger than the number of shared matches of our trio. The question is how much larger. In the example shown, we indicate that the number of shared matches of the dyad are larger than or equal to the number of shared matches of our trio. In the case of the unfavorable trio, the notation here indicates that the number of shared matches of the dyad are much larger than the number of shared matches of our trio. And so our differentiation value is the number of DNA matches common to all three subjects of our trio divided by the number of matches shared by our dyad. And if we replace our trio-specific letters with generic A, B, and C, we can write a formula for our differentiation value like this. However, because the trio formed by our three individuals remains favorable or unfavorable regardless of which elements we identify as our dyad, we actually want to evaluate all of the trio's three consistent dyads size and prefer the largest of these. Note that we also need to make a provision for situations where two of the trio's members are closely related. I'm not going to go into the specifics here, but we're basically addressing the two-legged stool issue, and the shared match differentiation process makes provisions in this regard by employing a separate dyad threshold to exclude dyads in our trio which are closely related. Whatever we do with our differentiation value, we need to conform to the centimorgan limits we established previously. So we'll add that stipulation here with the 40 and 400 centimorgan thresholds in the language of set theory. And finally, when we crunch all these numbers, we end up with a fraction. It's kind of a percentage. And we have to ask, well, what does that mean? And by analyzing actual DNA shared match trios from real DNA matches, what I found is that unfavorable trios tend to generate values at or near zero. In fact, the largest value I've seen is just under 4%, and I can speak to that separately. So my working definition of this is that anything greater than 5%, and the smallest value I've seen is more than 8%, is a favorable trio. Now, I call this process shared match differentiation, or SMD for short, and you can find a streamlined overview of the process, what it does and how to use it on my website. There's a QR code here to help you navigate to the site if that's simpler. Now, in our previous example, the shared matches of A and E, we would evaluate trios formed by A, E, and each of their shared matches. And based on the outcome of our formula, we determine whether or not to include that individual among A and E's shared matches. And again, we could opt to report every shared match and simply flag the unfavorable trios, or we could suppress the unfavorable trios if that's preferable. So here we have the differentiation value for individual B, and the differentiation value for individual C, and the differentiation value for individual D. And returning to our scoreboard, since these are fairly simple formulas to evaluate, especially for a computer to evaluate, we can give genealogical bioinformatics full marks for speed and accuracy. At least I'm going to. Now, you may wonder, just how would a commercial DNA testing provider incorporate something like SMD into their reporting structure? And the answer would look something like this. This is a process flowchart of the process I've discussed here, with a few things that I haven't fully discussed redacted. And the flowchart indicates what needs to happen for a programmer to incorporate shared match differentiation into a reporting structure, independent of whatever programming language the provider's backend server runs. Now, I realize this sort of diagram is probably incomprehensible to most genealogists, but to a computer programmer, it's actually quite clear because the SMD process can be distilled into a single page chart like this, it's the sort of process that can be easily appended into any reporting structure without placing an undue burden on your computer server's infrastructure. But let's say you don't run a commercial DNA testing provider. What then? And the answer is you can use what I call the SMD utility. If you're able to download the full sets of DNA matches for 3 individuals, you can use this utility to perform all the necessary calculations to tell you whether the individuals form a favorable trio or an unfavorable trio. And since in fact you could paste in the matches of 3 random individuals, the utility will also tell you if the individuals form no trio of any sort whatsoever. Now, the right-hand area in this image here shows the results of a couple of dozen shared match trios that I've tested with the utility just in this example. The green status indicates favorable trios, and you can see a couple of unfavorable trios that are listed there as well, typically with a differentiation value of 0, although again, there was one very unusual tree where I got a value of almost 4%, but that tree is an extreme outlier, which I can discuss later. You can see a QR code here on this image, which will take you to the page where you can download the SMD utility. It runs in Microsoft Excel. You can also download a quick start guide that steps you through how to use the utility. I previously mentioned that these bioinformatic processes are modular, that they're like a carpenter's tool set. They can be used in varieties of ways and in a variety of situations. I'm going to give you examples of some of these situations just to sort of give you a bigger picture of really what this little tool can do. One example is that SMD, or shared match differentiation, can evaluate larger collections of shared matches by breaking them into overlapping shared match trios. So if you had a set of 4, 5, or 6 or more individuals who appear to share a common ancestor, but you want to be certain of this before committing to building up trees for each of them, you could use SMD to verify whether they all share a common ancestral couple. And again, maybe only some of them do, not all of them. Now, here's an example. If we had a collection of 4 individuals, A, B, C, and D, who appear to share a common ancestor, you would evaluate them in SMD by breaking them into the following trios: ABC, ABD, ACD, and BC. C, D. And that covers all four elements there. If all four trios validate as favorable, then all four individuals share a common ancestral couple. Something like in this case here, I've taken from a set of DNA kits that I manage. All four of these individuals evaluate as favorable no matter how you combine them into different trios. However, let's imagine that only two of the trios validate as favorable. Then it's possible that individual C matches A and B along one ancestral line, while individual D shares a separate ancestral connection with A and B. And that would be something like this. Again, another example from one of my family trees where individual C matches A and B one way, individual D matches A and B from another line, and yet as a collection of four, they don't share a common ancestor. If we were to combine these examples to form a collection of five individuals, break five individuals into trios would require 10 different differentiation values to determine if they share a common ancestral couple. And so we could look at value 1, which combines A, B, and D. We could look at value 2, which is A, B, and E. Value 3, which is A, B, and F. Value 4, which is A, D, and E. Value 5, A, D, and F. Value 6, A, E, and F. Value 7, B, D, and E. Value 8, B, D, and F. Value 9, B, E, and F. Value 10, D, E, and F. Now, if we were to pass all 10 sets of trios through the SMD utility, only these bold values would actually come out as favorable. And the SMD utility can maintain a log of the trios as they're evaluated, so you can retain an audit trail of which are favorable and which aren't. And so without actually having built up the tree as I've done here in the diagram, you can at least get an idea of how people might and might not share common ancestors. And of course, although running through 10 different formulas is something that as humans would take us a lot of time, we have to keep things straight and make sure we haven't missed one. For a computer, this is very easy to do. And so you can get the idea of how we've expressed certain genealogical ideas in terms that a computer can just jump on and seize and make sense of and report back to you as to what the outcome is. And again, this is how, when we come back to the idea of letting AI solve some of our problems, these are some of the basic tools that AI might use, which we are developing now. Again, this is 10 formulas for 5 individuals, and there's actually a mathematical formula that tells us how many formulas are needed based on the number of individuals we have. This is kind of a probability distribution combination theorem, and you don't need to understand what any of this means because I've actually worked out what it happens basically for the number of individuals we have. So a trio only needs one differentiation value. We looked at our example of A, B, C, and D, and that required 4 different trio combinations. The previous example we had here used 10 formulas, and that was for 5 individuals. And you can see that as the number of individuals increases, we need more formulas. Again, that's something that's a burden for humans, but a computer can just whip through this stuff in a millisecond. And so the whole idea is to let the computer do the heavy lifting, and we just sit back and read the results. So to summarize what SMD can do, and again, you can find more information on my website through the QR code. SMD employs full sets of DNA matches to identify favorable or unfavorable shared match trios. SMD can also assess any collection of 3 or more individuals to determine if they share a common ancestor. With a little more coding, SMD could be used to validate existing family trees, again, to see if your genealogical work is corroborated by whether or not these people actually do share a common ancestor. And SMD can also take a collection of individuals without existing trees and generate a framework through which they might be logically connected. Again, something you would then need to prove through conventional genealogical research. Lastly, SMD can be used to proofread collections of individuals created or employed by other bioinformatic processes. And again, this idea is significant in that it encompasses some of the preceding points, but also hints at some of the broader implications for bioinformatics. In the course of crowdsourcing test materials to develop this process, some people ask me, why not try this work using triangulated segments and other things? My glib answer was always because bioinformatics. And by that, I mean that the mathematical underpinnings of this process ensures that all of our bioinformatic processes kind of exist in the same logical space, which is to say that having built the SMD process to distinguish between favorable and unfavorable trios, and having shown that that process can assess larger collections, we can think of SMD as kind of a self self-contained tool, the way you might think of a hammer or a carpenter's level or a saw as a self-contained tool which can nonetheless be used in a variety of circumstances. In a way, this is a modular process that can be plugged into other bioinformatic tools to enhance their functionality. And I'm going to give you a quick example before we wind up. Back in 2021, I filed my first patent application for this bioinformatic process I call CMA, which stands for Correlated Multiphasic Analysis. And while the specifics of that process would require a separate presentation, the basic idea is that everyone has a brick wall ancestor, someone for whom, try as you might, you can't find reliable documentation for. They don't turn up in other people's family trees. You don't have any obvious DNA connections to them beyond your immediate family. In short, they're an ancestor whose pedigree is essentially one big question mark. But what the CMA process does is it uses your DNA matches and your documented connection to your brick wall ancestor, and it uses the DNA matches of other known family members who are also descended from your brick wall ancestor, even if they're distant cousins or half relations, and it generates what I call a genetic complex, a collection of individuals connected to you through the pedigree of your brick wall ancestor. Now, CMA's genetic complex is just a list of individuals who share DNA exclusively with various combinations of the descendants of your brick wall ancestor. And you can see a sample of the list on the screen here, a collection of individuals who match our test subjects A and B in the range of 20 to 40 centimorgans. The purpose of this list is twofold. It provides actionable intelligence in the form of shared matches that you, the researcher, can investigate through traditional methods by building up trees, finding common surnames, localities, etc. Or you can take the list of individuals along with the full set of DNA matches for each of these individuals, and you can dump them into another process I built called ASK. And this is a process I spent about a year working on. What ASK does is it takes that information and it actually provides you with clusters of individuals that share a common ancestral line, and then it stratifies those collections so you can see which ancestral lines are more closely connected to your brick wall ancestor, either through the brick wall's parents or grandparents or so on. You would still need to do the genealogy to build up individual pedigrees to see how the individuals are connected, but at least you have focused collections that you can research rather than, say, a list of 1,000 individuals. Now, of course, there's a catch. Some of you may be familiar with this computer science term GIGO, which stands for garbage in, garbage out. And what this means is that the quality of data you get out of a process is a reflection of the inputs supplied to the process. Kind of you are what you eat, but for data processing systems. Now, what comes out of CMA is a list of individuals who match various combinations of the descendants of your brick wall ancestor. These are basically collections of shared matches. And like the shared match trios we've previously obtained from our DNA test results, these groupings of shared matches can either be favorable or unfavorable. If the shared matches are favorable, then ASK will be able to place the matches in the hierarchy shown in the diagram. And that's great. It's what we want to have happen. However, if any of the matches in our list are unfavorable trios, then those shared matches are going to cause ASK to kind of chase its tail, because it's a bioinformatics system that wants to organize your DNA matches according to points of connection around individual common ancestral couples, and instead we're supplying the process with some matches that have multiple connections, so it's simply not going to work. And so to clean up the CMA list, we can run it through the SMD process and scrub out the unfavorable trios. In the list shown, you'll see I've left the entry of the third name in the trio there unblurred, and this individual, we'll call him SP, shares 39 centimorgans of DNA with subject A and 34 centimorgans with subject B, but doesn't match any other descendants of our brick wall ancestor. Also, SP has a cousin MP who also matches A and B in similar amounts. When I developed CMA in 2021 and perused my list of shared matches, I contacted SP, as he has a well-researched family tree, and I tried unsuccessfully to discover our common ancestral connection before moving on to other queries. In the course of testing the SMD utility with a variety of shared match trios, I returned to SP's match with subjects A and B, and I ran the DNA matches of this trio through the SMD utility, and it flagged SP's match with A and B as an unfavorable trio, which pretty much explains how I couldn't find the obvious common ancestor I was looking for. So if we process CMA's list of shared matches through SMD before handing the list off to ASK, our confidence in the results of the ASK process will be greatly enhanced. Further, since SMD is lightweight and is a self-contained process, it can be employed wherever and whenever we need to verify the integrity of a collection of shared matches, as was the case here, where SMD was used to proofread CMA's list of shared matches before handing the list off to Ask. To wind up, in summary, just a few takeaway points. Bioinformatics is an interdisciplinary field of science that develops methods and software tools for understanding biological data, especially when the data sets are large and complex. Genealogical bioinformatics employs aspects of biology, information engineering, and mathematics to address problems in the field of genetic genealogy. The genealogical bioinformatic methodology provides a reliable framework for the investigation of genealogical problems and the development of bioinformatic solutions. Bioinformatic tools and processes can be engineered for computational efficiency for use with reporting systems in real time. And finally, bioinformatic processes can work cooperatively or independently, forming an extensible toolkit to facilitate the constructions of new processes and to improve the accuracy of existing processes. To learn more about this evolving area of inquiry, I invite you to join the Genealogical Bioinformatic Facebook group that I've created, which right now only has 2 members. Again, I don't expect anyone to rush out and start doing this stuff on their own, but what I'm very interested in finding are other problems in genetic genealogy which might lend themselves to this kind of solution. Often, again, you don't really realize a problem exists until someone mentions it to you, and then suddenly it's extremely clear as to what might be doable with it. I'm again very curious to see what people might get up to in suggesting new areas of research. I invite you to visit our website at discoveringnewancestors.com for downloadable resources and copies of the utilities I've discussed in this presentation, in addition to case studies and other interesting bits of digital data. So thank you, everyone.